Imagine flipping two coins in completely different cities. One lands heads, the other tails. They act as completely independent objects, driven only by local physics. Now imagine a pair of quantum coins, like two electrons, that have interacted and become entangled. They lose their individuality and become a single system. If you separate them by 1,000 miles and measure one, finding it spinning heads, that measurement instantly forces the other to land tails. Zero delay. No hidden messages are passed between them. It is an immediate reaction that shatters everything our daily experience tells us about how space and distance actually work. This concept was so unsettling that Albert Einstein refused to accept it was real. He famously dismissed it as spukhafte Fernwirkung, spooky action at a distance. In his 1935 EPR paradox, Einstein argued that because nothing can travel faster than the speed of light, this instantaneous link meant quantum mechanics simply had to be missing something. He proposed what we call hidden variables. He thought these particles must carry a secret, pre-written instruction set from the exact moment they were created, dictating exactly how they would behave later. If hidden variables didn't exist, it would mean objects don't actually have definite properties when we aren't looking at them. The idea of an independent, objective reality would collapse. To see why Einstein was wrong, look at this equation for an entangled singlet, a Bell state. It describes two particles as one object. Neither particle has a definite spin until measurement, when both instantly resolve into opposite states. In 1964, physicist John Bell created a rigorous mathematical test to settle the debate. He drew a hard line to see if those hidden, pre-written instructions actually existed. Following decades of work, incredibly precise, loophole-free experiments in the 2010s ran Bell's test. The results were completely clear. Nature violates Bell's mathematical boundaries. Hidden variables are a myth. Objects lack definite independent states, and the universe is non-local. Once physicists accepted the universe behaves this way, they stopped treating it as a philosophical problem and started treating it as an engineering resource. We now use this connection for quantum teleportation. We can transfer the complete quantum state of a particle from one location to another without physically moving the original particle at all. We also exploit it for quantum cryptography. By tying communication keys to entangled states, any attempt by an eavesdropper to intercept the data instantly breaks the entanglement, exposing the hack through the laws of physics themselves. Then there is quantum computing. By entangling qubits, which exist in a superposition of multiple states at once, we can explore vast numbers of computational solutions simultaneously. Harnessing entanglement alters the nature of computation, allowing machines to navigate vast solution spaces in ways classical hardware never can. This bizarre connection reaches past the laboratory and out to the macrocosmos. Through a theoretical framework known as the ADS-CFT correspondence, physicists are uncovering evidence that entanglement actually generates the geometry of space itself. The Ryu-Takayanagi formula mathematically links the physical area of a region in space directly to the amount of quantum entanglement on its boundary. This suggests that the physical structure of our universe is an emergent property. Geometry is simply entanglement expressed in a different physical language. If the entanglement between quantum regions were magically severed, the surrounding spacetime would literally pinch off and tear apart. Physicist Mark van Ramstonk described it perfectly. Entanglement is the literal thread sewing the fabric of the universe together. The distance between 2 points, or 2 distant galaxies, is an illusion. The universe has always been a single, holistic entity, whispering to itself across connections that no distance can break.